So for chapter 33, our topic is all about electromagnetic waves. And what we're going to do, we're going to start with reviewing something we've already talked about, something called Faraday's law. And basically what Faraday's law told us was that a changing B field induces an electric field. So if I change a magnetic field, I can make an electric field pop up out of that. Now this also works the other way. Works the opposite way. It works vice versa. So what that means is if I change an E field, then that will induce a B field. And this procedure is kind of something that's very common in science. It's kind of a positive feedback mechanism. Which means that as one variable changes, the other one does as well. So we can see how this works in the form of a very common type of wave. We'll talk about the most common type of electromagnetic wave, something called light. So light works because you take some kind of electrically charged particle and you make it oscillate. You make it move up and down. So we make this charge bounce up and down. So if it's bouncing up and down, then I'm creating an electric field that's going up and down. And then I can make this charge move forward. And this is going to give me an electric field that's going to kind of trace out a wave shape. So it's actually going to look like a wave. Electric field goes up, and then down, and then up, and then down, and then back up, and so on. And it will continue in this manner for infinity until it's stopped. Now this is going to represent our electric field. And it goes up and down, vertically away from some non-disturbed point, some equilibrium point for a wave, something we talked about in Physics 1. Now this E field is changing. We can see that very, very clearly. It's going up and then back down and then up and then down. So it's doing something we call oscillating. Apparently, according to what I just said, if I have a changing E field, that's going to induce a B field. And sure enough, it does, except the B field doesn't go in the exact same direction. It actually moves at 90 degrees to the E field. So we're going to try to draw this in 3D. It's kind of tough to see. But this B field is coming into and out of the board. So it's coming out towards us, if you can imagine that, and it's moving away from us, going into the board. So we're trying to see this in 3 dimensions. We can write this another way. We can write the E field as going in the positive and negative J hat direction, which means that this B field coming into and out of the board is going in the positive and the negative K hat direction. And we need to remember that this all started from this tiny little charged particle. Take a charged particle, make it move up and down. Because you're moving this charged particle, that creates an electric field. The electric field going up and down induces a magnetic field. E induces B, and vice versa, B induces E. We already know all of this. And this is a process called a positive feedback mechanism. So as one increases, the other increases, and because this E field is changing, there's always going to be a B field that constantly changes too. So what's the importance of this? The importance of these oscillating fields is that they create light rays. So an oscillating field, an oscillating electric and magnetic field, is what we call light. And the very useful part of this oscillating field is it can travel through empty space. So what does this look like mathematically? How do we actually use and apply this? Well, we need to derive some kind of law. We already know Faraday's law. Faraday's law of induction, we just learned that. And Faraday told us that the integral of E dot ds is equal to negative d phi dt. We're going to put a little b with that phi, because that phi is the magnetic flux. So it depends on a changing magnetic field times an area. So the change in your magnetic field is that flux. Now we can draw something similar for magnetic induction. This was changing magnetic field inducing an electric field. We also can do vice versa. We can do the integral of B dot ds. So again, we're drawing an analogy to Faraday's law, except this time our magnetic field is going to be induced, it's going to be changed by a changing electric field. It turns out we can derive this law. The integral of B dot ds is mu naught times I times epsilon naught is the derivative with respect to time of flux once again, except this time it's going to be electric flux. Now to get some practice with this, you should look at an example, and you should look and study very, very closely how example 1 works. And that will help you to kind of make sense out of this adjustment to Faraday's law for magnetic fields. But that's not the entire story, because this left-hand side, the integral of B dot ds, should look kind of familiar. So where does that look familiar from? It should look familiar from Ampere's law. And in Ampere's law, if we remember, Ampere's law tells us that the integral of B dot ds is equal to mu naught times I enclosed. But I just said that this magnetic induction, we'll call it B induction, is kind of the same thing. It's the integral of B dot ds equals mu naught epsilon naught times d phi dt. So which one is it? Which one is correct? Well, it turns out that a magnetic field can be induced by both both this current, and a changing electric field. And we should be careful and make sure that we specify that this is electrical flux. So we can combine these two equations and get to a new law, something called the Maxwell Ampere law, named after the two gentlemen that figured out these two different laws for how electricity and magnetism worked. We have Ampere's law, and then this magnetic induction law that was discovered by, you guessed it, Maxwell. So we get the final version of what we get when we integrate a magnetic field around the outer perimeter of a surface. The integral of B dot ds is equal to mu naught times I enclosed plus mu naught times epsilon naught times d phi sub E, so that's the electric flux, how the electric field is changing, dt. This gives us the Maxwell-Ampere law for electricity and magnetism inducing each other. So to stop for a second and summarize everything we know about E&M, everything we've learned this semester can be encapsulated into these 4 equations. These are collectively known as Maxwell's equations, because he came up with that very last equation, that very 4th equation, that kind of wrapped everything up into a nice bow. Our first equation, integral of E dot dA equals Q and over epsilon naught. This is Gauss's law. And conceptually, it means something very interesting. It's Gauss's law that comes from Coulomb's law. Coulomb's law is a direct result of this. And conceptually, this very first thing says that opposites attract and like charges repel. Then we have our second equation. Second equation, conceptually, it means there are no magnetic monopoles. This isn't named after a particular individual. It's just a realization that there's no magnetic monopoles in nature. Next equation, we have Faraday's law. And Faraday's law tells us conceptually that a change in B induces an E field. So magnetic field can induce an E field. And finally, we have the last equation that we just learned this chapter, the Maxwell-Ampere equation, which conceptually tells us that a change in an E field can induce a B field. And again, in practice, all these four equations, if we wanted to summarize exactly what they do, they create light. They make light possible. We have light because of the calculus that's contained within these equations. And we can create waves from these E and B fields, from the way these equations interact. We create E and B fields. And since we know now that E, a changing E, creates a B, and a changing B creates an E, as long as one of them is changing, the other one will change, and we get a positive feedback loop, which means that a wave will keep traveling forever. And since these two combine to give us light, we can find some equations that are relating these two quantities. And this was one of Maxwell's big contributions. He figured out that light travels at a particular speed. We call it c. C is the speed of light. It's around 3 times 10 to the 8th meters per second. And if we look at those constants that are in some of these equations that we're looking at, we can figure out that c is equal to the square root 1 divided by the square root of mu naught over epsilon naught. And these guys, these constants, they're in that Maxwell-Ampere's law. They work that way because the Maxwell-Ampere law actually describes how light waves work. It's a fundamental result inside of physics. There are some other equations that are very useful for talking about light waves. From Physics 1, or even from chemistry, we should know this equation C is equal to lambda times F, where C is going to be the speed that you're traveling, and in this case it's speed of light. Lambda is going to be how big your wave is. It's going to be your wavelength. We'll come back to wavelength a little bit at the end of this lecture. And then F is going to be the frequency, how rapidly your waves are shaking up and down. And we can draw a nice little picture of what this kind of light wave looks like. So what we have here is a picture of what a light wave actually looks like. Again, it's created by some charged particle, any kind of charge that you make move up and down. That creates an electric field, and I've drawn my electric field here in red, going up and down in the positive and negative j hat direction, and then that creates a magnetic field according to the Maxwell-Ampere's law. And this magnetic field B is going in and out of the board at 90 degrees to my electric field. So that has a very specific relationship. It's called being orthogonal. It means that E and B fields create each other orthogonal at 90-degree angles. And then, if I combine these two together, these waves can travel indefinitely through empty space. And they can travel in a direction that's perpendicular to both of them. So in this case, the direction that these waves are going is going to be perpendicular to both the j hat and k hat direction, and the only thing that's perpendicular to both of those is going to be the positive or negative I hat direction. If I want to figure out what direction things are going, what direction these waves go, I can use the right-hand rule again. I told you it never goes away. The electric field is going to be the direction that your fingers point on your right hand. The magnetic field is going to go in the direction that you bend your fingers. And then the direction that the wave actually travels, the direction of your actual motion, is going to be the direction of your thumb. So again, this is the right-hand rule. It's no different than the ones that we've been doing. Let's make this a little bit more clear. Fingers are again in the direction of your E field. You bend your fingers in the direction of the B field, and your thumb will be the direction that you actually travel in. So let's summarize some other nice, interesting features that we know about electromagnetic waves. Well, we can derive an equation, and we could do a lot of algebra trickery to get to this, but we'll just shove it right out there. Magnetic field is equal to 1 over c times E. A very useful equation. Other interesting facts about electromagnetic waves. E fields and B fields, because they induce each other, are always in phase. This means, by being in phase, that peaks meet with peaks and troughs meet with troughs. So what that means is, if I have two waves, the tops line up with the tops, and the bottoms line up with the bottoms. We're not going to get any kind of cancellation of a wave. Other interesting features of waves that we need to know: the size of a wave. Another way to think about that is the height of a wave from an undisturbed position has a specific name. This is called the amplitude. The amplitude of a light wave is going to depend largely on your electric field. Has another name. We can call this a plane wave. And that's the picture that I just drew on the previous little slide that you saw. And you can look at this in the book. The book pictures are a little cleaner than mine. These are going to be figure 33.11 and 33.12. And since we really depend on this E field, we have something else that we define a wave according to a wave. We define something called the polarization of a wave according to the E field. And the polarization is going to depend on the direction of your E field. So the direction of your E field tells you your polarization. So remember once again how we get a light wave. We take a charge and we maybe shake it up and down. And that's going to create an electric field. And that electric field is going to go, in this case, if I'm shaking up and down, it'll go up and down. So that's the direction of my E field. So my polarization direction is the same direction as that E field. So in this case up here, where I've shaken my charge up and down in the positive and negative y direction, this is going to be positive and negative j hat direction for my polarization. In other words, this can be said to be vertically polarized. And you probably know this word polarized from sunglasses. So let's see if we can understand how polarized sunglasses work. Now, normally, sunlight has waves that are in all different polarizations. So it's electric fields going up and down, shaking around left and right, shaking at angles to each other, and we're polarized in all sorts of different directions. So we have a variety of different directions that the electric fields are going. Now, if I want to polarize this light, maybe decrease how bright the light is, I can take some of these rays out. And I can take out rays in specific directions with things called polarizers. And this is how your polarized sunglasses actually work. So let's say that I have a wave, and it's got waves going up and down, electric fields going up and down, and electric fields that are going in and out of the board. So I have both vertical and horizontal waves. And then I can create a little polarizer. So let's say I create my polarizer, and this polarizer is only going to let in vertical waves. It's only going to let vertical waves through. So if I put that polarizer in front of my light ray, then these horizontal rays, we'll try to make it a little bit different with different colors. The horizontal rays are going to hit this, and they're going to be blocked. The only rays that are going to get through will do up and down rays, vertical rays in red. So the up and down rays are then going to get through. And I can block out a nice portion of the light. So instead of your sunlight being super bright, it'll now be about half as bright if it's only got up and down light waves coming through. And then if I want to block out all the light, I could take another polarizer, and I can orient this one horizontally. So this would only let through horizontally oriented light, horizontally polarized light. I've already blocked out the horizontally polarized light, so my vertical light hits this and gets completely blocked. And now no light gets through. And I've blocked out all light by using polarizers. And your polarized sunglasses do this. They block out either vertical light rays or horizontal light rays. So the last thing to talk about in this chapter is going to be the entire electromagnetic spectrum. So light is not just visible. We have a variety of different wavelengths. And I mentioned we'd talk more about wavelengths. And we can create the whole electromagnetic spectrum of all wavelengths that are possible. And we can divide this into regions. And we'll go over these regions in class with some examples, some interesting kind of fun examples. Let's step through these regions of the electromagnetic spectrum one by one. And what we want to do, at least what I want to do, is I want to rank these according to their energy. And energy is H times C divided by wavelength, or energy of a wave is equal to H times frequency, where H is going to be Planck's constant. So let's rank these wavelengths according to the electromagnetic spectrum and where they sit. First, let's talk about gamma rays. Now, gamma rays are going to be the smallest wavelength, which means they're going to have high energy. In fact, they're going to be the highest energy. And we can see this in our equation, E equals hc divided by wavelength. If I have a small wavelength, if my denominator is small, then my energy is going to be a bigger number. So what other parts of the electromagnetic spectrum do we have if we jump through according to energy? After gamma rays, we have the next smallest wavelength, we have X-rays. We know what these are. This is what you use to get pictures of broken bones. Above X-rays, we have ultraviolet rays, also known as UV. So these are going to be the period of the spectrum right before we get to what we're probably most familiar with, the visible portion of the spectrum. And this is going to be based on that famous guy that everybody should know, Roy G. Biv. Beyond the visible, we get to the infrared, the IR, also known as infrared. This is actually the wavelength that people glow at. And sixth, we have above infrared, we have microwaves. And last, but certainly not least, we end up with radio waves. And radio waves are going to be the longest wavelength and correspondingly the lowest energy. We'll talk about each of these in class more in turn. And as you'll notice, this chapter is very, very heavy on concepts, not so much on problems. So you'll need to study this up a little bit to really get these concepts sticking in your head.